Hello and welcome back. Let me just turn this a bit. Let's talk about a completely new thing to us, eigenvalues and eigenvectors. So any square matrix can have eigenvalues and eigenvectors. And we find them using this formula. This might seem completely new, and it is. Might seem completely random, and it is. But it's pretty simple, as long as we remember that this lambda is just a number. It's just a scale. So let's find the eigenvalues and eigenvectors of this matrix. Okay. Well, let's figure out what a minus lambda I is. Well, a minus lambda I is 3, 1, 2, 4 minus lambda times our identity matrix. Just the matrix with diagonal zeros. And what this equals is 3 minus lambda, 1, 2, 4 minus lambda. Pretty simple. Now, a lot of people are just going to skip to this step, and I don't blame you, because there's no point in writing all this out. You just subtract a lambda from each diagonal. So the determinant of this is just going to be this times this minus this times this. So 3 minus lambda times 4 minus lambda minus 2 times 1 is 1. Or 2, sorry. And we're going to set this equal to 0, as according to our formula. Now we solve this, we expand, and then we factor. What we're going to get is lambda minus 2 times lambda minus 5 equals 0. And what this tells us is that lambda can equal 2 or 5, of course. So lambda 1 equals 2 and lambda 2 equals 5. We don't want to say that lambda equals 2 and 5. We're going to say that lambda 1 and lambda 2 equal 2 and 5 respectively, because we want to be able to see that there's different ones. Okay, now eigenvectors. What are these? Let's solve for them. What we're going to take is this new formula. A minus lambda I equals 0 for all of the lambdas that we found. So remember that A equals, what was our A? 3, 1, 2, 4. Okay. So now we're just going to subtract lambda 1 from this and set it equal to 0. So 3 minus 2 is 1, and then we have 1, our 2, and our 4 minus 2 is 2. We're going to set this equal to the 0 vector. We use Gauss-Jordan elimination. It's a very simple Gauss-Jordan elimination. We get 1, 1, 0, 0, 0, 0. We have a row of zeros, which means that our x2 can be called a parameter. Let's call it t. And our x1 is negative x2, so it's just negative t. So we can say, in general, x equals t times minus 1, 1. And this vector right here is our first eigenvector. Boom. Now let's find the second eigenvector. Well, we're going to do the same thing, except this time we're going to subtract the second eigenvalue, which is 5. 3 minus 5 is minus 2. 4 minus 5 is minus 1. We're once again going to get a row of zeros. You should always get a row of zeros. And then we're going to get, let's say 1 minus 1 over 2, 0. So x2 is our parameter, and x1 is 1/2 of that parameter. X equals that parameter times 1/2 and 1. So that means that our second eigenvector is 1/2, 1. There's our eigenvectors, there's our eigenvalues, and that's really how simple it is. Now keep in mind, we can say that our eigenvector 2 is just 2 times itself, so it can be 1, 2. It's the same thing. Usually we take t equals 1, but t could equal anything, as long as it's not 0. That's just, we don't want that one. So thanks for watching this video. In the next video, we have something very exciting. I hope to catch you in it.